The Chapter 6 practice problems look at empirical formula and coming up with an empirical formula if you are giving masses of elements or percent composition of elements. So let's look. Our first question gives us three molecules and asks about an empirical formula. So an empirical formula, let's define that. An empirical formula, when we represent a compound using its empirical formula, that is the smallest whole number ratio of elements. And so smallest whole number ratio of elements. So however we can express this compound using the smallest ratio of elements. Okay, so for this we'll build a little chart with the molecular formula. Then we're going to solve for the empirical. And then we're going to put on here the factor. So the factor is whatever we have to divide through by to turn something from a molecular formula to an empirical formula. If given the factor, you can also take an empirical formula and then multiply through to get the molecular formula. Okay, so the first molecule given in the practice was C2H6O2. So this is the molecular formula. This is the atoms needed to make this molecule, but it's not, we can represent the ratio of elements with smaller numbers. So if we look through here, we can divide through by 2. So our factor here is 2. If we divide through by 2, we get C with a 1, which we don't put. 6 divided by 2 gives us 3. And then 2 divided by 2 gives us 1. So our factor was 2. We divide these through by 2 to get this empirical formula. Again, if we had to go the opposite way, we could take these and multiply through by 2 to get the molecular formula. Okay, so our next one was C12H22O6. Okay, so if we look at what we have here, looks like this one is also going to have a factor of 2. So if we divide through by 2, we have 12 divided by 2 gives us a 6. We divide through by 2 here, we get an 11. And then if we divide through by 2 here, we get a 3. So this is our smallest ratio of our elements here. But we had a factor of 2 to go from one to the other. Okay, our last one is HNO2. So if we look through here, since these are both 1, there's nothing we can divide through by to reduce these down. So they are the same. So in this case, the empirical formula and the molecular formula are exactly the same because they're already in the smallest whole number ratio. So that is true. Sometimes something is already in its lowest whole number ratio and you can't reduce it down any further. Okay, so problem number 2 asks us to find the empirical formula of a compound that is 5.888 grams of calcium. It is 4.710 grams of sulfur, and it is 9.402 grams of oxygen. Okay, so we want to find the empirical formula of this compound. So when you see the word empirical formula, this is telling us a mole ratio. So we're expressing them as a formula with subscripts, but really we're saying for every 1 carbon in this molecule, there's an oxygen. And for every 1 carbon and oxygen, we have 3 hydrogens. So that's all we're doing here. We're just going to figure out what the mole ratios are. So this is a problem of mole ratios. So to make mole ratios, first we have to turn all of these into moles. So that's what we're going to do. So 5.888 grams of calcium. So to turn it into moles, we have 1 mole of calcium for every, look this up, 40.08. So 40.08 grams of calcium. Okay, so our calculator, so we have 5.888 divided by our 40.08 gives us 0.14691 of calcium. Okay, so next we're going to do our sulfur. So 4.710 grams of sulfur. So same thing, 1 mole of sulfur. So if we look sulfur up, we have 32.07. Okay. So 4.710 divided by our 32.07 gives us, oh, looks very similar. So 0.146, we'll call it 87 mole of sulfur. And then last, we have the oxygen. So we have 9.402 grams of oxygen. So 1 mole of oxygen for every 16 grams of oxygen. Okay, so last one, 9.402 divided by 16 gives us 0.5876. We'll keep one more, 63 moles of oxygen. Okay, so now we want to make make mole ratios from this. So I'm going to take these moles and use them in the sort of chemical formula. So I'm going to put Ca 0.14691, and we have S 0.14687, and we have O 0.58763. So technically, this is our compound. We just need now to turn these into whole numbers. So what we're going to do is we're going to divide through by the smallest one. So since these are essentially the same, we're going to divide through by one of these to see if these ratios have 1 as that they're all based off of something having 1. So like for our examples up here, if we would divide our moles through by the lowest one, if this was our empirical formula, since we have a 1 here and a 1 here, we're going to get our empirical formula. So that's not going to work for this one here, and we'll talk about what we would have to do at that point. Okay, so I'm going to divide all of these through by the smallest number, 0.14687. Okay. So when I do that, I have 1 for calcium, I have 1 for sulfur. So now I'm going to take my oxygen and divide it by the 0.14687. And when I do that, I get the whole number of 4. So my empirical formula is CaSO and 4. So all of these two reduce to 1. And when I divide it through here, this gave me a 4. So we have CaSO4 as our empirical formula. Okay, so let's look at the third one. So the third one gave us percentages instead of masses. So in the third one, we are given that we have 44.44% nitrogen, we have 4.80% hydrogen, and we have 50.76% oxygen. So now we want to find the empirical formula given mass percents. So what is nice about these percentages by mass is that it doesn't matter the mass of the compound. These percentages always hold true. So if we have 20 grams of this unknown compound, those percentages would be valid. If we had 100 grams, we would still get these exact same percentages. It doesn't matter the mass. So to make life easiest, we assume that there is 100 grams of the compound, whatever it is. We're going to assume there's 100 grams of it. This will make life easier because we can use our percent by mass. So recall that percent by mass is equal to the mass of element divided by mass of compound times 100%. Okay, so we're going to use our percents here. We're going to assume we have 100 grams of the compound, then we can solve for our mass of our element by doing that. So we'll have 44.44% nitrogen equals mass of nitrogen, we'll call X, divided by the mass of the compound, which we said we were going to assume was 100 grams, times 100%. So we have 100 divided by 100, which gives us as X is equal to this now in terms of grams. So X is equal to 44.44 grams of nitrogen. So when you assume that you have 100 grams of the compound, all your percents are going to turn into the mass of the elements in grams. Okay. It doesn't have to be 100 grams. You could have chose 20 here. You would just have 20 right here, and you would have to work through the math here to get your mass of nitrogen. So whatever you assume this is, it has to be true for all of them. If you assume 100, it's 100 for all of them. If you assume 20, it's 20 for all of them. Okay. So X is this for nitrogen. We could set this up for all of our other ones, and we would see that hydrogen is 4.80 grams of hydrogen, and oxygen would be 50.76 grams of oxygen. Okay, so now that we have our elements in terms of grams, everything is identical to the previous problem. We're going to take these. We want to find the empirical formula, which is mole ratios. So we're going to take these and we're going to turn them into moles. And so we'll start with nitrogen. So we have 44.44 grams of nitrogen. So nitrogen, we have 1 mole of nitrogen per 14.01 grams of nitrogen. Okay. So 44.44 divided by 14.01, that gives us 3.1720 moles of nitrogen. From there, we're going to do the same thing with our hydrogen. 4.80 grams of hydrogen. 1 mole of hydrogen for every 1.008 grams. Okay, so 4.80 divided by 1.008. So we get 4.7619. And then finally, we can look at our oxygen. We have 50.76 grams of oxygen, 1 mole of oxygen for every 16 grams of oxygen. Okay, so last here, so 50.76 divided by 16 gives us 3.1725. Okay, so it looks like, similar to our previous problem, that these two are the same. So whatever moles of nitrogen we have will be the same as for oxygen. Okay, so I kind of want to note just as all percents have to add up to 100. So if you add all these up, we get 100%. Our masses here add up to give us our 100 grams as well. Okay, so now we're going to just do mole ratios again. So we're going to have N, 3.1720. We're going to have H, 4.7619. And we're going to have O, 3.1725. Okay, so we're going to take our nitrogen. We're going to divide everything through by 3.1720 to get our mole ratio. So this will give us 1. So we have N. So let's look at our hydrogen here. So we're going to have 4.7619 divided by 3.1720. So I divide by that, I get 1.50. So H 1.50, and then I have O. Okay, so I don't want to round. I don't want to take this and say, oh, it's close to, what is it close to? It's kind of almost right in the middle. It could be closer to 1, or it could be slightly closer to 2. So we don't want to round. So this should sort of scream out to you that it's a particular fraction. Okay, so what this means is if you go through and you divide through and you don't get a whole number like we did here, that means that the subscript of one of these here is not 1. So just like, again, if we go back to our empirical formula problem, so since these ones had subscripts of 1, we're able to simply divide through and get our mole ratios. If you look at this one here, we do not have one of them that's 1. Okay, so we have a 3 to 6 to 11. So in this one here, when we divided through, we would get a fraction, just like we did here. So you have to figure out what you can multiply through by to turn this into a whole number. So since it's 1 1/2, we can multiply through by 2. Okay, so we can multiply through by 2. So 2 times 1 gives us N2. So 1.5 times 2 gives us a 3. And then 2 times 1 gives us a 2. So we have N2H3O2. So we didn't have, again, a whole number here, which told us that our ratios, one of these subscripts was not a 1. So we had to multiply through by 2 to turn them all into whole numbers. So that's how empirical formula works. We're looking at mole ratio. So when you're doing these problems, if they give you a percent, easiest to assume you have the 100 grams. So you can use, so our percents turn directly in to the mass of elements in grams. Turn all of those into moles, that's very important, and then build your mole ratios to get your subscripts.